Alright, so hope everybody is doing great. So here we have a radioactive sphere. So since we have a nuclear reaction, a nuclear fission going on inside the sphere, there is going to be a heat generation term. We're no longer dealing with transport without generation. Now we're going to have both molecular transport and generation. We're going to have a generation term, my fellows, ladies and gentlemen. So give this problem a read. All right, one, two, three. I hope you guys have read it. So let me read it with you guys. A radioactive sphere, as I've mentioned, is cooled by air at a temperature T infinity. Okay, cool. This nuclear fission reaction leads to heat generation, like I mentioned, and the heat generation may be modeled as this expression right here. I've given you the units. The units are energy per volume. Energy per volume. The cooling with air may be modeled as Newton's law of cooling. So we're going to be using the heat flux equal to Q. By the way, lowercase q is heat flux. H times the temperature at the radius. Temperature at the radius of the sphere minus T infinity. So that's going to be my boundary condition, one of my boundary conditions. But we'll talk about boundary conditions later. Derive the temperature profile. Okay, profiles. We always have to derive profiles in transport phenomena. So let's go. Let's go at it. So start off by assuming, like a good engineer, assume stuff. The stuff that I'm assuming is that we have steady state, and steady state means that every partial derivative with respect to time is going to be zero. No change with respect to time. Constant thermal conductivity. K is constant. Good. That's going to help me decide which equation I want to use, which heat conduction equation I want to use. Heat transfer only in the radial direction, only in R. That means T is going to be a function of R only. T is not going to depend on, in this case, theta and phi. Those are I'm talking about spherical coordinates. But before we jump on to coordinates, let's look at our heat equation, the heat conduction equation. Okay, and this is the heat conduction equation with a constant thermal conductivity and a source term and no flow. We are not dealing with convective, advective transport right now. So let's see. Boom, bye bye. Why bye bye? Steady state. So the equation is going to look something like this: negative source term divided by conductivity equals the Laplacian of the temperature. Hello. Look at that boy. But this is vector notation, and as you guys probably know, most engineers look at vector notation. They're like, ugh. So we're gonna since we have a sphere here, we're dealing with a sphere. We're gonna jump into spherical coordinates. Yay! So this right here, I took this, and this right here is the Laplacian. This is the Laplacian and spherical coordinates. This is the Laplacian and spherical coordinates. And let's see. I know that temperature is only a function of R. That's what I know. Temperature is only a function of R because there's only heat transfer. Q is only in R. There's only heat transfer in R in radial direction. And what does that mean? Bye-bye. Adios. Temperature is not a function of theta. Temperature is not a function of phi. Temperature is a function of radius. All right, let's go. So if you guys remember the source term, it was negative. It's gonna be negative a over k times 1 minus. Let's see. Capital R. By the way, uppercase R is the radius of the sphere. Okay, let's see. And that is gonna equal. This is the only term that survived. Okay, the radial term is the only one that survived. So let's switch colors. And now my partial derivatives are going to become absolute derivatives because temperature is no longer a function of other variables, only a function of R. Right, boys and girls? Right? Oh, and I was missing a square here. Silly me. Let's switch some colors. Actually, I want my independent variable to have a different color because hey, I like colors, and I heard Gen Z likes colors too. I mean, that's what I heard. I'm sorry if you don't like it. And okay, the next part is gonna be integration. Now it's just an ordinary differential equations problem. The next part is gonna be integration. And just to give you guys a foresight, we're gonna have two constants of integration. So we're gonna need two boundary conditions. My first boundary condition is gonna be at r equals 0, dr is going to be equal to 0. Why is that? Because flux at the center in curved coordinates, in cylindrical and spherical coordinates, flux at the center is going to be 0. It's going to be 0 because it's going to cancel out. It's going to be 0. Okay. And r equals capital R. Oops. R equals capital R being the radius of the sphere. Negative k dTdr, the heat flux at R equals capital R is going to be Newton's law of cooling. So heat transfer coefficient times temperature at R equals capital R minus T infinity, the temperature of the air. So this is where I'm gonna end this video. All right, so I'll see you guys in the next part of this video. Thank you.